IB HLAA, day number 5, probability and statistics. Today we're going to talk about Bayes' theorem, which is an extension of conditional probability. Now I'm going to show you a formula used for Bayes' theorem, and then I'm going to show you the practical use of it. So no intimidation factor here, but by definition I'll show you Bayes' theorem in just a moment. Before getting into Bayes' theorem, I'd like you to attempt this exam style question. I'm going to go ahead and allow you to pause the video like I have control of you or something, but I'd like you to pause the video and attempt this and then come back when you have either a stumbling block or you've completed the problem. Okay, so I'm going to continue mission here, assuming that you have paused the video and now you're back after your attempt. So it says John goes sailing every day in July. To help him make a decision on whether it is safe to go sailing, he classifies each day as windy or calm. Given that a day in July is calm, the probability that the next day is calm is 0.9. There's a conditional probability there. Given that a day in July is windy, the probability the next day is calm is 0.3. The weather forecast for July 1st predicts that the probability that it will be calm is 0.8. So let's go ahead and do the following. Let's draw a tree diagram to represent the situation for the first 3 days of July. So part A, I'm going to go ahead and start with a tree diagram. Here is July 1st. July 1st could be calm or it could be windy. July 2nd, again, calm or windy. Calm or windy. July 3rd, again, calm or windy, calm or windy. Just like the 3-child family, there will be 8 possible outcomes on July 3rd, or at least built on July 1st and 2nd. Okay, so what we're told is that the probability that July 1st is calm is 0.8. Okay, so if you look at this stem of the graph, July 1st is calm, July 2nd is calm, July 3rd is calm. The probability that July 1st was calm was 0.8. And when one day is calm in July, the probability the next day is calm is 0.9. Now I have that happen twice in a row, right? So here we've got a calm day, so this would be 0.9 followed by another 0.9. Okay, so I'm going to build all the probabilities within this table and then explain them. I'll explain them after I build them off camera. Okay, so you can see as we build this potential scenarios, there are 8 scenarios. Each has their own percentage or probability. And they're built off the information above. So let's just pick one randomly. Let's take this one here, 0.056. So the probability it's calm on July 1st is 80%, 0.8. Okay, now the probability that we have a windy day following a calm day is 0.1, right? Because the probability that we have calm followed by calm is 0.9. So these two values here will be complements of each other, right? 0.9, 0.1. Okay, now the probability that we follow a windy day with another windy day was 0.7, or the probability that we follow a windy day with a calm day is 0.3. So you can see all the way through this that the values are complements of each other when you branch off to the next option. Okay, so I get the probability that July 1st is calm, July 2nd is windy, and July 3rd is windy to be about 5.6% or 0.056. Okay, part B states, now we can get into some probabilities. Part B states, find the probability that July 3rd is calm. The probability that July 3rd is calm, we can highlight with the following 4 probabilities. July 3rd is calm in that scenario, in this scenario, and this scenario. I don't care about July 1st or 2nd. All I care about is July 3rd. So the probability of each of those added together would end up being 0.7 0.68. So a 76.8% chance that July 3rd ends up being calm. All right, now let's take a look at part C. It says find the probability that the 1st of July was calm given that the 3rd of July is windy. Okay, so let's talk about this conditional probability idea. The probability that the 1st of July was calm given that the 3rd of July was windy. Remember that that's the probability that both happen over the probability of the latter event. Okay, so for A, I'm going to define A as July 1st is calm, July 1 calm, and B as July 3rd windy. Okay, so let's find the numerator here. Probability that July 1st is calm and July 3rd is windy. Well, I see this as having to be on this half of the diagram and terminating here and here. So that guarantees that July 1st is calm and July 3rd is windy. So I'm going to add those two values together, which are 0.072 and 0.056. When I add those two together, I get 0.128. Now I need to find my denominator. So when is July 3rd windy? Okay, so I include all potential scenarios where July 3rd is windy. So I include the two I built the numerator with, but I also include the two for when July 1st was windy as well. So if I add up those four values, I get 0.232. And so the probability that July 1st is calm given July 3rd is windy, based on my calculator, gives me 0.552 or 55.2%. There you have it. Let's get into Bayes' theorem. Okay, Bayes' theorem, that is a total mess. Now, believe it or not, this right here is equivalent. It is equivalent, and I'm not going to go through the derivation in this video, but it is equivalent to this. Okay, so my best way of thinking about this is if you're interested, go ahead and explore that. Okay, go ahead and explore that on your own time. I might make a video deriving that, but let's just get into more conditional probability with multiple events. So what we just did on the last slide with John and his sailing was actually what we're going to do on the remainder of the notes. We just didn't know it yet. So Bayes' theorem applies here to each of the situations you'll see as follows. So example 2, two machines, A and B, produce widgets. Machine A produces 40% of the total widgets. So let's go here, say machine A, 40% of the total widgets. Machine B produces 60% of the total widgets. Okay, 3% of machine A's widgets are defective. So these would be the defective widgets coming from machine A. That means non-defective widgets or functional operational widgets would be 97% that come out of machine A. Machine B, 5% are defective and 95% are operational. Okay, so I could build my probabilities based on that. I'm just going to choose to answer the questions here, but I typically format it by putting each of my probabilities right here and then working the questions afterwards to keep a nice organization about my work, but I'm just going to go ahead and work the questions. A widget ready for shipment is selected at random. What is the probability it is defective? So a defective widget, right, would show up in one of these two spaces, right? So I guess I can model what I'm talking about and add 0.4 times 0.03 plus 0.6 times 0.05. So 0.4 times 0.03 plus 0.6 times 0.05 comes out to be 0.042 or 4.2%. So there's a 4.2% chance that a randomly selected widget is defective, not knowing which machine it has come from. Okay, part B, here's where the Bayes theorem piece comes in, right? Because that was just independent events, right? I added together those two events to see what the probability was that one selected widget was defective. Let's look at the second question. A randomly selected widget is defective. What is the probability that it came from machine B? So when we build this, what we want is, given that this is defective, what is the probability it came from B and is defective? So B and defective would be here, this probability, over defective, which is what we have already highlighted in question A. So we're going to take 0.6 times 0.05 and divide it by 0.4 times 0.03 plus 0.6 times 0.05. Okay, so with that being said, we get a 0.03 in the numerator, and we already knew this answer from above was 0.042. So given that a randomly selected widget is defective, what's the probability it came from B? It comes out to be 0.714, or we could say 71.4%. All right, that's Bayes' theorem in action, right? You're building this denominator using this. Without even knowing it, you're using that. Okay. All right, so let's get into another example, again using Bayes' theorem. The probability that a person has a rare genetic disorder is 0.005. So a person has a disorder, and the probability they don't have the disorder would be 0.995. The probability that the individual had a true positive test is 0.95. Probability that they've been deemed to have the disorder, but the test was false, is 0.05. So these folks right here don't actually have the disorder, even though the test has told them that they do. Likewise, a true negative happens 80% of the time, a false negative 20% of the time. So these individuals here don't actually have, or they do actually have the disorder. They're told they don't, but they do actually. Okay, so let's look at the two questions that are posed. Part A, find the probability a randomly selected person gets accurate results for their test. So this would be the probability that someone has a true positive plus the probability that someone has a true negative. Okay, so let's build those probabilities. That would be 0.005 times 0.95, as could be found right here, plus a 0.995 times a 0.8, which can be found right here. So these are the folks that actually got a test that was accurate. All right, part B. Given that the test determines that a person does not have the disorder, what is the probability they actually do? Okay, so these folks here have tested negative. Whether it's a false negative or a true negative, it doesn't matter. Okay, so they believe that they do not have the disorder, but some of them actually do. Right? These people actually do have the disorder. So to find the probability posed in part B, to find that probability, what I'm going to do is I'm going to take the blue value, which is those that actually have it, okay, and I'm going to divide it by the sum of those two red values. So these are the people down here. They don't think they have it. They don't, quote unquote, have it. These people actually have it. Okay, all right, so let's build that. The blue value is going to be 0.796. Okay, that would be 0.995. 0.995 times a 0.2. Whoops, miscalculation. That ends up being a 0.199. Okay, and we're going to divide that by 0.199 plus whatever this value comes out to be here. So 0.995 times 0.8, which is 0.796. All right, so given that the test determines that a person does not have the disorder, the probability they actually do ends up being about 0.8 or 80%. Okay, this is Bayes' theorem. Now, this can sometimes be a little confusing along in the process, but try to keep it straight. Try to keep your definitions of what each of your symbols means. So negative here, positive here, and then T and F along the way, and what those mean in the context of the problem. Let's do one more problem, and we'll be good for this lesson. Okay, Josie has 3 ways of getting to school. 30% of the time she goes by car, 20% by bike, 50% of the time she walks. Okay, that's going to be the first stem of our tree diagram. Now this is a 3-decision tree diagram, or 3 routes, right? 30% of the time she rides in the car, 20% of the time she rides bike, and 50% of the time she's walking. Okay, when traveling by car, she's late 5% of the time. So she's not late the other 95% of the time that she rides in the car. When she bikes, she is late 10% of the time. So the other 90% of the time there, she's not late, she's on time. When she walks, as predicted, the following apply. Okay, so let's look at the question here. Given that Josie is on time, find the probability that she rides her bicycle. Okay, so let's write this out. Probability that she rides her bicycle given that she's not late. That would be the probability that she rides her bike and is not late over the probability that she is not late. Let's build each of those and find them accordingly. Okay, so the probability she rides her bike and isn't late, right, would be here. So that probability would be 0.2 times 0.9. Okay. And the probability that she is not late would be each of the following. Not late, we're going to overlap it with this and then use that as well. So we'll take 0.3 times 0.95, which ends up equaling 0.285. So 0.285 plus 0.2 times 0.9 is 0.18. 0.18 there. And our last value would be 0.5 times 0.75, which is 0.375. Okay, 0.375. And then, of course, in our numerator, we're going to use this value again. So I get 0.18 over 0.84, which ends up equaling 0.214 or 21.4%. So given that she is on time, the probability she's riding her bike is 21.4%. All right, guys, that's it for day number 5. See you in the next video.